Welcome. In this video, we will explore the architecture of a custom stochastic system dynamics Monte Carlo simulation of our solar system's economy from 2026 to 2076, coded in Rust. We designed this model to study how Earth's economy integrates with expanding off-planet space automation, dynamic geopolitical frictions, and artificial general intelligence adoption timelines. Over the next 12 scenes, we will walk you through the codebase, the unique memory safety mechanisms, parallel concurrency optimizations, macroeconomic deflation algorithms, and decadal portfolio solver mathematics that power this high-performance simulation. Let's examine the baseline structural state. In Rust, we represent this using two main data structures, PolicyConfig and MarketState. PolicyConfig holds the active governance parameters, such as tax and tariff rates, state-subsidized R&D rates, and AI adoption timelines. MarketState tracks our running 5-decade simulation, storing variables like planetary GDP, corporate liquidity on Earth, and stock valuations of the primary space conglomerates SpaceX, Rocket Lab, and Lunar Outpost. These structs form the robust, static foundation of our system dynamics modeling. One of the most unique aspects of Rust is its zero-cost abstractions and highly optimized memory layout structure. In our PolicyConfig struct, the name is stored as an immutable string slice with a static lifetime annotation. This tells the compiler that the name resides directly inside the compiled binary payload, avoiding heap allocation and runtime pointer overhead. Additionally, fields are packed sequentially to minimize padding bytes on the stack, ensuring that spawning millions of parallel MarketState paths consumes a minimal memory footprint with absolutely zero garbage collection pauses. To achieve high performance across 5,000 Monte Carlo runs, we scale the simulation concurrently using Rust's native operating system threads. Because the compiler strictly enforces the send and sync traits at compile time, we are able to copy or share state representations between threads with a 100% guarantee of thread safety. This eliminates any possibility of a runtime data race. Each native thread processes its allocated slice of simulation paths completely in parallel, utilizing all available processor cores with zero lock intention or runtime execution overhead. One of our most interesting mechanics is the stochastic event role, covering what we call the high ground advantage. When governments try to nationalize off-planet infrastructure, the risk of retaliatory corporate secession is modeled using a mathematical sigmoid threshold. If the space economy dwarfs terrestrial output, corporate defection succeeds, and government nationalization is permanently disabled. This mechanic creates a dynamic power balance between terrestrial sovereigns and space-based conglomerates. Our simulation manages geopolitical friction using a detailed temporal state machine. If an off-planet secession commences as a hostile embargo, trade exports are capped at just 20%. However, this embargo does not last forever. An internal counter tracks the years, naturally cooling the friction down into peaceful trade cooperation after exactly 10 years. Concurrently, regulatory FOMO checks simulate a 5% risk of severe AI regulations, which accelerates defection corporate flight, or a 25% chance of complete deregulation as nations race for survival. Let's explore the simulation's macroeconomic deflation modeling. As artificial intelligence reaches full white-collar exploitation and massive off-planet energy beams saturate Earth, deep supply-side deflation is triggered. While falling prices benefit the real purchasing power of citizens, it devastates governments holding massive national debt. In our model, nominal GDP collapses while the nominal debt burden remains fixed. This causes the real value of the national deficit to balloon rapidly, driving terrestrial sovereigns into severe liquidity deadlock and credit default traps. Here is our Rust implementation of this sigmoidal transition. The formula maps the space-to-Earth GDP ratio to a probability curve. A scaling multiplier of 4.0 controls the steepness of the transition around the midpoint. If our stochastic role succeeds, the off-planet corporations secede and transition to a sovereign state status. In Rust, we ensure mathematical safety by explicitly handling division by zero cases, immediately returning 100% defection probability if Earth's GDP collapses to zero. Now, let's step into the details of our decadal portfolio optimization mathematics. Every 10 years, the engine executes a multi-asset grid search. For each weight candidate, we compute the return and volatility. We determined the portfolio beta, which measures sensitivity relative to traditional benchmarks, and the portfolio alpha, representing excess annual yields over CAPM expectations. We then seek the target weights that maximize our Sharpe ratio, using a risk-free rate of 2%. Let us review our native solver implementation in Rust. Every decade, we iterate through candidate weight configurations from our candidate weight array, verifying that their sum equals exactly 100%. The algorithm evaluates the historical decade-end values across all 5,000 paths. It computes the average yields, covariance matrices, and Sharpe scores. If a combination records a Sharpe rating higher than our current best, it updates our active allocation structure. Why did we choose Rust for this high-speed simulation pipeline rather than Python or C++? The safety benefits are overwhelming. Rust's compile time verification guarantees that we avoid memory corruption and out-of-bounds pointer reads, which are notorious in C++. Meanwhile, its compiled nature allows us to process millions of complex mathematical operations per second, leaving Python far behind. Rust's strict error handling via the option and result enums ensures there are absolutely no unhandled panics or crashes in production, making it ideal for institutional financial simulation. Compiling this simulation in Rust yields a high-performance optimization engine capable of processing millions of stochastic paths in seconds. Now that we've traversed our core algorithms, we're ready to compile the model, run tests, and examine the decadal recommendations generated by the code.